can make shirts for the week. Like, we could probably make them for like 6 months.
Okay, let's get started. Today we have the ASME crowd here to tell you a little bit about the Professional Society for Mechanical Engineering, and then we'll get into the lecture. So why don't I just hand it over?
Get the PowerPoint one. How's it going, guys? So who here is ME? Raise your hands. Okay, so kind of a lot of us. This presentation is geared towards you guys. For civil, there's a professional society for basically all of them. So mostly everything goes for everyone, but we are specific to ME. So why join ASME? It's a great way to get involved on campus here. You meet a lot of people in all your classes. You make friends. You know, you can do study groups with them, that sort of thing. And you know, you learn from your peers, so it helps in all your classes. It's a great opportunity to do networking. We do tours and that sort of thing of local engineering companies. We have people come in and give lectures, well, not lectures, but like kind of informational talks, that sort of thing. You can ask them questions afterwards. So it's a good way to meet people in the industry. And so that kind of goes for internship and career opportunities. You can turn that networking into a job. And finally, we do projects such as the Human Powered Vehicle, HPVC, Human Powered Vehicle Challenge. And that's basically, they make, it's more or less a bicycle, but they put fairings on it, you know, that sort of thing, make it as aerodynamic as possible. And then they go and compete in April. There's also the super mileage vehicle, which is, oh, sorry, I'm kind of stealing your thunder here, actually. Anyways, special projects, and here we go, I'll hand it off.
Like Alex, the president of ASME already stated, we do the Human Powered Vehicle competition, and our next meeting for that is tomorrow at 6 p.m. And if you have any questions or want to talk to anyone, talk to the project manager, Logan Ingersoll. And I think last year we were 6th in the West, overall 6th, and then the year before that we were overall 6th, so hopefully this year we'll be better than 5, because I guess the canoe team for civil is 5. We kind of got to beat the civils. So, yeah. And then the next one that we're starting up this year, this will be the first year we're doing this. It's a super mileage vehicle, and it's a competition to provide engineering technology students with challenge design projects. And your main goal is to make a vehicle that can go really far and really small mileage. Right now we're looking for a location to actually begin the construction of the SMV, but they are on Facebook, UNR SMV, and their next meeting is Monday at 5:30 in the ASME Lounge, which is PE, Palmer Engineering, 211. And then if you want to email Tarj, that's his email address right there. Okay, now this is what I'm interested in. We also don't have, those are only 2 competitions and vehicles that we are making currently, and the ones that I want to start making are either Formula 1, and that's actually my old school, and their Formula 1 car, University of North Florida, and then here's a Baja car that's also interesting to make. And so these are the competitions we're looking forward to making, and we're trying to get your interest in them, because we can't do these competitions just us 3. We don't have the time. We don't have we don't have the knowledge. We need your help. So, our next meeting is Thursday, September 27th at 11 o'clock in the morning. Tomorrow. Yeah, tomorrow. It's in LME 315, which is also the building right next to this one. Take up 3 flights of stairs. This is going to be an introduction to what ASME is. We're pretty much going to be looking for your feedback, what you want to see us do, and like what you want to get out of ASME. Because truthfully, everyone that has a position in ASME was elected Friday. So we're all new, we're all trying to figure out what you guys want, and we're all trying to figure out how to make ASME pretty much better than ASC. So, okay, sorry, I'm not supposed to talk. I'm not supposed to trash talk. Oh, and here's Russell, our vice president.
I just want to say that regardless of what project you are, if you are civil, you're chemical, whatever you choose to be, you can still participate with any of these challenges. All you need to do is actually register with ASME. So I just wanted to clarify that anybody who wants to can participate.
Yep, absolutely. And you should. That was the last one. Okay.
All right, that's it.
Okay, so that first one is tomorrow at 11 o'clock. And I know that room where that meeting is going to be is not all that large, so if you can get there a little early, you might actually get a seat. So we'll see. Okay, reminders. Typically, we do this at the beginning of class, but some of it's getting a bit old. Rental kits, as you know, you can pick them up, 50 bucks, pay for it first. Journals, get in the habit of doing that every week. Now, as Dr. Volstead mentioned on Monday, you have a couple of big things that are due pretty soon. These are, we call them major activities, but we're really sort of talking about team activities. You have your preliminary design report. That will be due pretty soon. And then 1 week after that, you're going to have the first checkpoint where you have to show us that your calculations are completed, that you've figured out what you need, which exact things you're planning to buy. You're going to come to the checkpoint, show us all this stuff, and we'll give you the go-ahead to actually go out and purchase these things. So please try to get those taken care of. Now, as it turns out, your design report is due a week before the checkpoint. So what that means is at the design report, you're probably going to have a lot of estimates and things, or hopefully you won't have a lot, but you probably have some where maybe you haven't finished all of your calculations and you still have a week before you really have to have them done. The design report should have as good an estimate as you can make for what fans you want to buy, what batteries you want to buy, all the attending doohickeys that you want to make the rest of your hovercraft out of. You might not know the details, but you should know enough to make an educated guess and then come up with an estimate of what it's going to cost. Okay? And that's what we're looking for in that report. By the time you come to the checkpoint 1 week later, you should have pretty hard and firm numbers. Those are the things that we're going to be approving that you're okay. That's how we're going to be judging whether you're ready or not. Preliminary report, you're going to have more latitude. Now, for that report, that's going to be due I think it's a week and a half, something like that. You're going to be handing that in this lecture. So you're going to be printing out, actually you're handing it in two places. First you're going to bring it to the lecture, and by 4 o'clock, so when we start talking at the beginning of class, we're going to have stacks of your things on the front over here. And if I see anyone coming up here after 4 o'clock, after we've started the lecture, that's going to be late. So please, when we say 4 o'clock, we mean 4 o'clock. All right, so please bear that in mind. And later on, after that, by midnight of that same day, you have to upload a copy of that report into Web Campus, using the attached file thing that you've been using for some of the other assignments. So please remember that. Please try to keep that in mind. There is a safety quiz out there right now, due next Monday. A couple of you have spoken with me about not being able to get access to the second part of the safety quiz. I've looked, people in the other room who talked with me after class on Monday, I looked into it and I can't reproduce the problem, so if you're listening, hopefully you are, come over to this room after class today and come on up and talk with me. We'll see if we can't sort it out. And hopefully that'll relate to anybody who's had trouble finishing the safety quiz. I know most of you have been able to do both parts, so I'm trying to figure out whether we have a big problem or not, because obviously everyone has to do that by Monday. And then finally, please watch the soldering video before the skills lab next week. If you haven't had your skills lab this week, there are going to be videos for that also. This skills lab that you're doing this week, the MathCAD and MATLAB, is one of the tougher skills labs of the semester because most of you haven't used either of those software packages before. Most of you have had something to do with Excel in your past, but MATLAB and MathCAD are usually a little bit new for engineering freshmen. I would probably recommend that do your best. The TAs are going to do their best to help you get up to speed on it, but the way you learn that stuff is to actually do the homework, to search through the software, figure out how to do things, come into the EDL and ask the TAs your questions, and they'll be able to walk you through things right on the spot if you have questions about that kind of thing. Question in the back. The question was, if a team has a team member who can't pay for the rental kits, what do you do? Well, the bottom line is everybody's expected to be paying for this course's participation in the same way as you would if it were a textbook. If there's a required textbook in your math class, you should be paying for that. And overall, in defense of ourselves, the overall costs of this course are much lower than a typical physics or math or chemistry textbook or something like that. So, short answer is everyone's expected to pay their part. If they can't, then the rest of their teammates, I guess that's sort of what's being implied. Does the rest of the team have to pick it up? Say, well, that shouldn't happen. Everybody should be paying their equal part. Okay? So if there are more complex difficulties, you can come and see either Dr. Volstead or myself, and we might be able to talk about it. But we expect, I mean, it's a requirement to come to UNR that you have to be able to pay for your books. So I know that sounds kind of crude, but that's the way it is. We don't have free kits to hand out or anything like that. Come on. There we go. Okay, first clicker question of the day. So, once again, to try to reward those who have actually been reviewing the notes from the previous lecture. What is a Gantt chart for? More particularly, how are you expected to use it in your design concept report, which is going to be due pretty soon? Yes. Yeah, I'll say that out loud. Okay, couple seconds left. All right, good. Wow, it was either easy or everyone reviewed. Okay, so just to reiterate, a Gantt chart is actually a pretty powerful tool that in the fields of engineering, you are most likely going to be using more Gantt charts than you know what to do with. Most modern industry and businesses use Gantt charts to help projects stay on track. They help plan not only where the effort is going, but you can also make the Gantt charts much more complicated where it's not only human resources that are tracked, it's financial resources, it's accesses to testing facilities and things like that. And it helps an organization stay on track as best as they can. So there are much more sophisticated tools to make Gantt charts than you're going to use in this class. If you're interested, well, most of you are probably going to use Microsoft Excel to make Gantt charts. And I put a couple videos on the website that'll walk you through how to do that in different versions of Excel. And you can find many more on YouTube. But if you're really interested in learning how to do this well, and you might do this by the time you get to your senior design projects, for example, there's a software package called Microsoft Project that specializes in making really cool Gantt charts and really detailed Gantt charts that you can take a look at. We don't expect that you use that in this course, but you guys, everyone in the College of Engineering, has access to free copies of a lot of Microsoft software. I mentioned that several weeks ago. Microsoft Project is one of them. It's like a $500 software package. You guys can get it for free. You can check out the instructions that I sent out in a course announcement maybe 3-4 weeks ago. And it's got a little bit of a learning curve, but it's quite powerful. All right, what is... Okay, I already talked about the checkpoint. One of the follow-up questions I had here during the quiz, one second, was when you're uploading your report, does everyone on the team have to upload a copy? The answer is no. One per team is all that we need. And you know, we will go down the list when we're doing the grading to make sure that we get one submission, at least one submission, from each team. Was there a question over here? The question was, is the Microsoft project free for a limited time? yes, because you're going to graduate. It's free as long as you're a student. Okay? Once you are no longer in the College of Engineering, I guess technically, once you no longer have an ECC login, Engineering Computing Center, then you won't be able to actually download it. Okay, we already talked about that. So today I want to go over hovercraft dynamics and control. And the broad topic of dynamics and control is actually a fairly advanced thing. And this is what's covered in upper division, junior and senior courses, especially in chemical engineering, electrical engineering, mechanical engineering. You do quite a bit of control. Dynamics is probably principally in the mechanical engineering, also in some in civil. But all fields of engineering need to have some sense of this. And you guys definitely need a basic primer on this when we're talking about figuring out and how to predict how your hovercraft is going to behave and preferably take advantage of certain things so you can actually control it. All right? So this is probably going to be one of the harder parts of your project for this semester. Getting it to hover, frankly, is the easy part. Getting it to go down and come back, that's where the challenges really are. So first phenomena that you're going to have to come to grips with is friction in these hovercrafts. As it turns out, because we are requiring that you have a rigid plenum underneath it, no flexible skirts and things like that, you're not going to have anything dragging on the ground. On one hand, it makes it a little harder to control, makes it more challenging to control. But on the other hand, you don't have to worry about friction so much. So the things that are touching the ground, if your hovercraft does have friction, it had better be because you bumped against a wall or because you have stabilizers, and we'll talk a little bit more about that later on. Stabilizers are legal, but you can't have your hovercraft dragging on the ground. So in principle, you're hovering, and there shouldn't be any friction between your hovercraft and the ground. And the sidewalls, you probably don't want friction with the sidewalls because that's going to screw up what direction you're heading. When you hit the sidewalls, it starts spinning, and it bounces off in a different direction like you're playing air hockey with it. So the general goal is to try to avoid hitting things with the hovercraft. But we'll talk about it in any event. Now, there are two basic types of friction. You probably studied this in high school physics or something like that. If you haven't had high school physics, you'll certainly cover it in physics here at UNR. Static friction is the friction that you have to overcome in order to begin motion from a stop. And dynamic friction, or kinetic friction, I should say, is the type of friction that you get after you're already moving. And the classical example of this is your car. When you're driving down the road and a deer jumps out in front of you and you slam on the brakes, if your wheels lock up, your tires are actually sliding across the pavement. All right? That kind of a friction is a kinetic friction. It's friction that you get while moving. But if you pause and think about the technologies that we have in cars nowadays, we have ABS system, anti-lock brake systems. The whole idea behind an ABS system is to prevent the wheels from locking up. I remember when these systems first came out, me and my friends, I was like in high school or something, and we had debates about, we just didn't believe that not standing on the brake pedal would actually slow you down faster. And any race car driver will tell you that you want to be able to get as close to the point where your wheels are sliding as you can, but don't cross that line. If you can get to that point, you will get the maximum braking capability of the vehicle. And race car drivers actually yank out the ABS systems from their cars because those are too conservative. They can't get close enough to the limit. Okay? They want to get even closer to that limit of locking them up, and they're skilled. They know how to do this because they can get even more braking force. Because, as it turns out, as long as those wheels are turning, they're not sliding against the road. And we actually call that a static friction case. All right? When the wheels are rotating on the vehicle, you can actually get better braking than when they're locked up. Okay? As it applies to a hovercraft here, once again, you're probably not going to be dragging much on the ground with the hovercraft, so hopefully that's not going to be an issue. But many of you will have friction issues to deal with depending on how you get your propulsion system working. Some people are going to move objects around on their hovercraft. And if you have to move something around with a really wimpy motor, friction is going to be a big deal. So you might want to figure out how you're going to address that. Other people are going to have stabilizers that have wheels on them that roll on the ground. Wheels work really well in one direction. They don't work so well in the sideways direction. So in those directions, the friction is actually a good thing. Right? Your hovercraft, you want it to go straight ahead. Right? You don't want it to go sideways and hit the sidewall. So having friction keeping you going from the sideways direction actually can be a good thing, helps guide you down the course. So please keep those in mind. And these are phenomena, issues that you're going to have to deal with when you're working on your control system. Friction can be good and friction can be bad. It all depends on what part of your system you're trying to deal with it. So you as a team have to figure out how serious it is. Is it really a problem? And in some cases, it might actually be desirable. Because we don't allow you to use flexible skirts, it's probably not going to be a big problem as long as you're actually hovering. Probably not going to be a big problem on dragging on the ground. If you're dragging on the ground, you're disqualified, right? So obviously, you have to design around that whole situation. Okay? The only way you're going to be able to figure out whether you have a friction issue anywhere on your hovercraft, on the top, dragging on the bottom, with your wheels, or if you have wheels to help keep you tracking in a straight line, is by testing it. And you won't be able to do this until you have something to test. So you have to build something, get yourself started, and get a feel for how much friction you actually have in your own hovercraft. Some hovercrafts, this is a zero issue. And in other people's hovercrafts, because of the design that they chose, they did have to spend quite a bit of energy or time thinking about how they're going to solve these problems. Other classical problems we typically have are spinning. Now, this isn't a physics class, but you might imagine if you have a hovercraft here with fans that are pointing straight down, the moment you turn those fans on, they're going to start rotating, right? And if this thing is hovering, there's essentially no friction between your hovercraft and the ground. And you have a rotating fan on it. What's going to happen is while the fan starts to turn clockwise, the whole rest of the hovercraft is going to want to turn counterclockwise, right? This is Newton's laws applied in a angular momentum sense, right? So the spinning of hovercrafts is a big issue that you have to come to some sort of a solution for. And how you achieve this is going to vary from team to team. Some teams will buy special fans that actually have two parts that rotate in opposite directions. So in other words, they have two fans stacked one on top of each other. You have to look for these carefully if you want to buy them. The top fan rotates counterclockwise, the bottom one rotates in the opposite direction, and they cancel each other out, and the rest of the hovercraft doesn't rotate at all. Okay? Some fancy helicopters use these types of stabilization techniques. Most of them use tail rotors, but some helicopters will do this kind of a thing. It is a particularly big problem if your hovercraft develops. It doesn't even have to be anywhere near this much spin. It only needs a little bit of spin because you're driving down this course that takes you 10 seconds to go down, right? And if you only have a slight spin, as you go down the field, suddenly your tail is spinning out, right? And you no longer are driving in a straight line down the course. Now you're driving into the sidewall. And once you hit that sidewall, then there's friction. And that friction gets you spinning really big time, okay? These are fairly significant challenges. You're not going to, I shouldn't say you don't want to challenge. You don't want to spin. Some of you might have designs that go down to the other end of the field and then do a 180 and then drive back in the other direction. Their spinning is actually desirable if that's your design, okay? But you want to make sure you turn 180 degrees and not 160 degrees, right? Or 140 degrees or whatever. The things that you can do to help address the spinning, either to cancel it out so that you don't have any, or to take advantage of it because you need it to actually turn around and go in the other direction, are everything from the balance of your overall hovercraft, where the fans are placed, how many you have, can sometimes influence it. If you have one, it's easy to put it on the center line. If you've got 3 or 4 fans, you might need to find the sweet spots where you put them so that it's not only balanced for the mass, but it's also set up in a way that the moments, and when you take dynamics, you'll learn about the details of this, but the moments created by the fans are all equidistant from the center of rotation of your system, and hopefully can cancel each other out. Right? The venting of the air underneath your plenum chamber can influence spinning. If you're not careful, it can be in a little exhaust port that gets you spinning really good, like a pinwheel. All right? Let's see here. Stabilizers, steering fans. These are other a little bit more exotic. Most people use these approaches to actually manage their spin. Some people will put rotors on the back end that help stabilize them, but that's a pretty complicated solution. They basically make their hovercraft stabilize the way a helicopter gets stabilized over here. I don't know if you ever thought about the complexities of a hovercraft, but if they didn't have the tail rotor here, the rotation of the main rotors would cause a reaction of the whole body of the helicopter to rotate in the opposite direction. And that's a pretty sure way to get really dizzy and then die. So they put a tail rotor on the back end that causes the rear end to get pulled in the direction that's opposite to the direction that the main rotor wants to force the whole thing to rotate. Okay? It's a fairly delicate balance. You have to make sure that your tail rotor is turning at just the right speed. This is actually one way they can actually point the helicopter in a direction that's different than the one it's actually moving. So you can have the helicopter pointing that way, but it's flying that way because of the clever things they can do with these tail rotors and the angles of their main rotors. Obviously way beyond the scope of this class, but some people I've seen try to put a tail rotor onto a hovercraft, and it can work, but it requires a fairly complicated feedback control system to actually get it to work reliably. That's the key word, with the reliability aspect. And I'll talk about feedback control briefly in a little bit. Ducting sometimes can do that. The biggest problems you're going to have are when your fans are pointing straight down underneath your hovercraft. Okay? That's the biggest problems for spinning, I should say. Another approach is to have that fan pointing sideways, but use ducting to redirect that air to go down underneath you. You might be able to reduce the effects that you get because of the rotational moments that get set up in this system. So a lot of different techniques. You might even just use stabilizers on the ground that add enough friction so it doesn't spin. Question, straight up back. The question is, if you use an axial versus centrifugal fan, do you get the same issues? The short answer is you can. It will depend on the orientation that the fan is mounted in everything. Okay? Basically, if the rotation axis of the fan, and I guess also the motor in the fan, they're not always the same thing, is lined up in the vertical axis of your system, you tend to run into some trouble. Okay. Okay. Obviously, balance of everything should be good. We talked a little bit about this earlier, maybe a week or two ago. I can tell you that the first thing you're going to want to do in your design process is get the darn thing balanced. In fact, I think it's checkpoint 2, where you have to have something built and hovering in place. Maybe it's checkpoint 3. You have to have it hovering in place. Namely, you have to have it balanced. This is going to be a recurring problem for you throughout the whole semester, because every time you make a little change to your hovercraft, you're going to throw off the balance. Or on Monday, you assembled it, you put your battery pack here. On Wednesday, when you met again as a team to work on it, the battery pack was off by 3 millimeters, and suddenly it's no longer balanced. Okay? Meaning that it's swerving, it's not hovering even, it's dragging an edge. You probably want to think about a design in which it's easy to balance on the spot, right? It's kind of like calibrating it, setting the gun sights before you go to the range. You don't want your balancing process, let's put it this way, you don't want to epoxy everything down onto your plenum, onto your platform. Okay? You don't want to make it permanent. You want to have some adjustability to it. And what we typically see are they'll put all their major components on board, and then they'll have ballast. They allowed for an extra 6 ounces, whatever, in their design, that they will put someplace on their hovercraft to get it balanced. But they included that in their mass budget and in their calculations. And they don't know where it's going to end up on any given day. Probably it's not going to wander too much, but it will probably not be in exactly the same spot. You don't want to bolt it down, most likely. Or if you do bolt it down, you want it to be easy to move to a different place. Velcro is one approach. Others will just use double stick tape and then just move it around. It's up to you. Okay. But if it falls off during a competition, then your hovercraft is technically touching the ground and you're disqualified. So you don't want it to fall off. But in the process of falling off, it would probably get knocked so far out of balance that it wouldn't work anyway. Okay, so the basic design point when we're talking about balancing your hovercrafts is that you're going to have a geometric center of your plenum chamber. The footprint, it's usually the footprint of your hovercraft. And you're going to want that geometric center, which is where the center of the pressure, of the air pressure that's lifting your hovercraft. You want that to be aligned directly below the center of mass, center of gravity, center of weight, whatever, of your hovercraft. This situation here would not be balanced, where the center of your weights are not lined up directly above the center of your pressure that's acting in the upward direction. That's what's lifting you. Okay? So this is one way you can sort of visualize it. This sketch, we call this a free body diagram. And those of you who go into most of the fields of engineering will be learning about this when you take statics. You might cover it a little bit also in physics. Okay, so I asked a similar question a few days ago. Testing your intuition, but we've talked a little bit more about it now. What direction is this hovercraft going to drift? Or is it going to drift at all? So this is a simple square, and I've drawn dashed lines to outline where the center of the square is. That's the footprint of the hovercraft, the plenum chamber. Hurry up. 5 seconds. All right. So the answer is that it's going to move in the forward direction. Okay? Recall, we talked about this briefly a few lectures ago. Okay? Oops. Recall this little sketch that I gave, where we have a hovercraft with some kind of a weight located on it. Ideally, when everything's balanced, you're going to have equal airflow going out all sides of the hovercraft, which is essentially going to keep it, all these airflows are going to cancel each other out, essentially, and it's just going to hover in place. But if we shift that mass to the side, we're going to tilt the hovercraft a little bit. The gap height on the left is going to be a little bit smaller, maybe a lot smaller, than the gap height on the right, causing more air to go out the right. We're effectively creating more of a jet effect coming out the right that's going to push everything over towards the left. Okay? This is a phenomenon that a lot of people take advantage of with their hovercrafts, but you still have to know what this center balance location is, right? Because you're going to have to be able to show us that your hovercraft can hover in place if we ask it to. Right? During the actual competition, it has to be able to go in a straight line, so you don't want it hovering left or right, but maybe you intentionally want it to hover in the forward direction. Right? That might be a good thing. But when you get to the far end of the field, you have to turn around and come back in the other direction. Right? So you have to be able to control these types of effects. And sometimes you can do it through weight shifts, and other teams are going to use more sophisticated techniques to do that. Okay, controls. Controls, as I was hinting at before, is a fairly complicated subject matter. You can have all sorts of different types of controls. But for these hovercrafts, we're going to talk about some fairly specific things that you probably are going to want to care about. In this class, we have an autonomous system. So we're controlling it, but not with a human. Right? That's what the autonomous part means. It's without human control. You have to be able to make a system that either controls itself mechanically or electrically, namely with some sort of a computer that will allow you to do the actual controlling. So, control systems are varied. There's many, many different types. There are open loop, there are closed loops. There's all sorts of different techniques that we generally cover in more advanced courses. But for this class, the control systems you're going to be using are actually a little bit advanced. We're not going to tell you why. We're not going to worry about the theory and all that stuff. But you're going to be making a full feedback control system. Probably is going to be controlled using a small microprocessor. You're going to be using sensors. You're going to be using motors or actuators, all sorts of things, maybe relays in this case here. So we have to look at our hovercrafts as a system that is controllable, meaning that it's not something that's just going to work at random, okay, where you need to be able to exert some kind of influence over it, or maybe have the computer exert that. You're controlling the computer, and the computer's controlling the actual hovercraft. Okay? The things that we are typically doing with the hovercraft is we're using sensors to detect where the ground is. Maybe you don't really care where the ground is, but you want to know what color the ground is, because the different parts of our competition board are either white or they're black, or silver actually in some cases. And you might have a strategy that needs to know where it is. You might not need to know exactly where it is, but you do need to know, are you at the finish line, or are you at the turnaround zone at the other end? So you need to know certain things about the environment and about the state of your hovercraft. Am I currently in forward? Am I currently in reverse? Or if I'm at the turnaround zone and I'm still going forward, something's got to change. All right? So these thought processes you have to build into your hovercraft in a way so it can exert control. Okay? Following the ground, well, that's not hard to follow it, but figure out where you are, that's almost a navigation issue. Following the walls, because we're not actually wanting you to touch the walls, we've put speed bumps on the walls, okay, in this class. So you can touch it, and I don't think there's actually a penalty for touching the wall. There's a penalty for touching the back wall, but not the side walls. But you will most likely screw yourselves up if you hit the side walls, because it's going to get you spinning, okay? Or a lot of times we have teams that were just slightly off-center following the center line, and they drifted just slightly, and they wedged themselves into the wall. In the styrofoam, where you can kind of just envision the sound. It's just sticking in the corner, and they get stuck there. And they don't keep going. They don't come back. They're done. Okay? So being able to detect where the walls are is sometimes a good thing. You don't necessarily need to have a GPS or compasses and things like that. Not for this assignment, but that's a big issue in other types of projects. Okay, quick video here. Let's see. This is a cat studying to become a controls engineer. My cat just simply unrolls all the toilet paper. But this cat sits there and plays for 10 minutes, flushing the toilet over and over and over. So quite curious about the way things work. But one thing this cat, Fluffy, realized was that the toilet always had the water come back, and it never overflows. Right? This is a very elegant example of a I don't even know how old this particular design is. A very old design of a control system. Okay? It is a mechanical control system. I don't want to give you guys the impression that control systems have to have computers and electronics and all sorts of stuff. A simple low-tech toilet is a very elegant example of a mechanically actuated and mechanically sensed and a mechanically controlled device. And we have lots of them. Cars are really good examples. Lots of the things that you have in a car are mechanically governed. Okay? So open your mind, so to speak. As modern engineers, we think, just throw an electronic circuit at it. It'll solve everything. And you can get electronic toilets. I'll show you a picture in a little bit. Right? Not necessarily the easiest or even the lowest cost or even the best things to do, but we tend to use controls as electronics nowadays. Perhaps not always a good thing. So a control system, and I'm using more lofty engineering language here, so bear with me. A question up front.
So just a quick question. You were talking
I don't want to tell you what you're going to want to do. Okay, the question was, if you don't want to hit the sidewalls, does that mean you have to put a weight in the middle to keep it from moving left and right? And I don't want to tell you how to do things. I will tell you, you probably don't want to touch the sidewalls. Okay, so I know that's not as helpful as you were looking for, but I don't want to drive what your designs look like too much. Okay. Okay, so control systems, and again, this is, I'm trying to use the more formal engineering language here for a little bit, are typically involving a selection of things. And the first three of these are probably the important things: sensors, actuators, and control, either mechanisms or circuits. But to that, we should probably add a couple of other features or characteristics that should be there. And each of these does not have to be a separate device, a separate physical thing. You can have a control system in which the sensors are built into the actuators. In fact, the toilet really is one example like that. It's hard to tell where the sensor ends and the actuator begins in a toilet. Okay? So, sensors. The idea behind a sensor is that it has some way of giving you a measurement of the system or the state of the system. It might mean your device, or it might mean the surrounding environment that you're trying to react to. Like a really simple example of a control system would be the thermostat in your house. You set it to a certain temperature, right? It's got a sensor, a thermometer. Okay? It's sensing what? The temperature of what? The house, okay? Is it sensing any other temperatures? It might be. Some don't. Some just say, it's cold, turn it on. Others say, it's cold, but the thing I'm heating it with is not up to temperature yet, so I'm not going to bother to turn on the fan. We have a forced air system in my house, and the furnace doesn't turn on the same time as the fan that circulates the air does. Okay? Those are two things. It doesn't start circulating the air until the air is actually warm. Otherwise, it's just blowing cold air around the house. Okay? So you can get simple systems where it's either on or off, and you can have much more sophisticated things. But the idea is that they tend to involve sensors. It detects something about the state of the system. And the system is a generic term that we use here that, in our case, in this class, it's a hovercraft. In your car, it could be the cruise control. In your house, it's the thermostat. Okay? These are all different interpretations of what the system is. An actuator, that is a generic term for something that is causing an action in your system. It's usually causing a change of some sort. The fan gets turned on. The heater gets turned on. Or for your hovercraft, maybe you're turning on a fan or turning off a fan or something like that. Okay? Where it's causing a change in the state of the system. So you measure the state of the system and you influence it somehow. Now you have sensors and you have actuators. Somewhere in there you have to have the ability to interpret what's going on, make decisions, cause the input that comes from your sensors to be interpreted and then something to happen as a result of how you interpreted it. It's cold. Well, it's cold. I want to do something about it. I'm going to turn on the heat. So I'm going to tell the fans and the heaters to get turned on or something like that. Okay? These here are done through what we call the actual controls in the system. Controls, again, oftentimes these days they're electrical in nature, but they don't have to be. A toilet is a classical example of one that's not. Mechanical mechanisms are well, they've been around a heck of a lot longer than computers. Control systems generally have power, and this bottom one is a little bit more nebulous, but it tends to be a pretty big deal. A fail-safe refers to anything that could go wrong. In the real world, you can't possibly make something truly fail-safe where nothing could happen that wouldn't cause a disaster in one form or another. Okay? Fail-safes have to be interpreted based on the circumstances. The fail-safe in a car and the fail-safe in an airplane look very different. Like in a car, if something goes wrong with the engine, what do you do while you're driving? Right? Odds are, unless it's catastrophic, well, heck, even if it is catastrophic, the engine stops, it seizes or something like that, and you just coast calmly to the side of the road, and hopefully you don't get run over by the cars in back of you, right? Fairly benign. What happens if the engine in an airplane seizes? You don't just pull over to the side of the road, okay? A fail-safe in that case might mean pull out the parachute or something like that. So in these situations, aircraft are a much more sophisticated situation, but what constitutes a fail-safe can really vary. What's a fail-safe in a toilet? What was that cat pondering? Right. The failure mode was that the tank wouldn't stop filling and you'd start overflowing your toilet. Okay? That would be a problem. So in that case, the fail-safe would be that if something corrodes and gets jammed, or if the valve doesn't open, or if you've got a little kid who keeps playing, or a cat that keeps playing with the lever, that it doesn't keep filling 5 times over and trying to fill the tank with 5 times more water than only fit 1. All right? So all of these interpretations of what is fail-safe will really vary depending on the situation. But we typically build these into the control system as much as we can. We don't want to have complicated ways of judging if something has broken. In the real world, that's sometimes impossible, and you have to have these complicated ways. But these happen. And classical examples, look at something that has failed in the real world, space shuttles catching on fire and blowing up or something like that. In those situations, they put as many systems as they could to detect problems. But sometimes you just can't do anything about it. Right? And in those cases, you can either spend a lot of money trying to do something, or you put a little consumer warning at the bottom in fine print, do not light this on fire, or something like that. Okay, so I've been alluding to the toilets. Okay, this is a good question for engineers. Raise your hand if you have taken off the lid from the back of your toilet at some point in your life and looked in there to try to figure out why the damn thing won't stop flowing, or whatever. All right, okay. All right, you're going to be engineers. You're on the right track. Okay. Raise your hand if you actually figured it out. Good. All right. It's an elegant and somewhat sophisticated device here. Now, this isn't Toilets 101. You can YouTube that to see it. But the idea here is that you have a tank full of water. Now, I'll caveat to that there are a lot of different toilet designs. This is the one that's most common in the United States, at least, where you have a water tank that holds water above the rest of the tank, so you get some hydrostatic head, and you have potential energy from all this 5 gallons of water being located about 1 or 2 feet above the business end of the telescope. Of the toilet. Telescope. Yeah. So when you push on the lever, or when your cat pushes on the lever, it lifts up this little plunger valve down here that opens up this opening right there. Okay? Water starts dumping down through that. It flows through the rest of the toilet. It creates a siphoning effect that draws the water out of the bowl of the toilet and everything with it. And it's a fairly elegant solution to be able to get the flushing action that gets a lot of water all moving at once and to take away all the stuff that you want to go away. Right? So, as you know, this all happens in a fraction of a second when you hit that valve, or maybe 2 seconds. But the toilet's not done with its business, right? It's going to have to reload, so to speak. And the way it does it, as the water level drops in the toilet, this float valve, this is basically an empty cylinder, it's floating on the top of the water. As the water level drops, this thing floats and it drops lower and lower and lower and lower. And at some point, the water level goes all the way down to the bottom, and the float is way, way down at the bottom. And it's attached to this lever arm. When it gets to the bottom, it says, okay, all the water is gone. Now I want to refill it. Okay? So this lever arm that the float's attached to opens up a valve that lets in fresh water. In the U.S., it's actually drinkable water, whether you knew that or not in the U.S. Here in Nevada, that's an issue. We have a lot of gallons of water that we're using drinkable water to flush our toilets in an area where water's at a scarcity like Nevada. Go figure. All right. As the water starts to fill back up, the float valve starts to rise again. And when it gets up to the top area here, it turns off the water valve and it stops flowing. Okay? So it's a fairly sophisticated sensor system. It's got sensors, actuators, controls, power. Where does the power come from in a toilet? The water. We call it the water head. Okay? The potential energy of the water in the tank and also the potential energy from the pressure coming from your supply water. Okay? That's where we get power from. So when you say power, we don't necessarily mean electrical power. Sometimes you have to plug your toilet in, but usually not. If you got the heated seat, for example, you got to plug it in. Right. Fail-safes. Well, that float valve is one way to fail-safe. Once that thing floats up, the only way this thing will truly fail and overflow the tank is if this thing stops floating. Okay, so I guess it's not truly fail-safe, but if one of your valves gets jammed or gets stuck open or corrosion happens, that ball is probably still going to keep floating. It's hard to make something not float, for that matter. Question? Yeah, that was implied when I said that you have a water pressure in your supply water. That came ultimately from a pump, usually, but sometimes not. It might just be that it's coming from a reservoir that's located 600 feet above your house, right? And then you don't even need a pump. Yep. But you're thinking, right, there are lots of ways that you can get energy into this system. Okay. So here's a picture of a toilet. I mean, who really needs a light in their toilet? Really? You got a problem if you're inspecting it that closely. They got heated seats. They got like water jets and all. Oh man, I mean they. Okay. Does an elevator have a control system? So think about our definition of a control system. Are all of these things present in one form or another in an elevator? All right, clicker question. All right, we're running short on time here. All right, good. The controller in an elevator is usually making decisions because they usually have sensors in them to tell them what floor they're at, right? Right? Have they reached the floor? If you've ever been in an elevator where it opened like a foot above the floor or below it, something's wrong with the sensor or with the control system, maybe with the actuator, right? So elevators are generally going to have all of these things. In our case here, we have a hovercraft that we want to be able to control, all right? We have to pause and think about what things we stand a chance of actually doing anything about with a hovercraft, right? We have things like the position to be worried about, what direction we're pointing. You might be interested in knowing how fast you're going, because if you're going really fast and about to hit the back wall, that's good to know how fast you're going. Are you rotating? How fast are you rotating? All of these things are important. Hovercrafts have 4 degrees of freedom. Right, guys, we're almost done for today, but please bear with me. Forward, reverse, left, right, up, down, and rotation. These are all the 4 different degrees of freedom that you have. And you have to decide as a team which ones you should be caring about. Right? The up-down direction, you might not really care about that so much. That's up to you. Maybe you do. There's a good reason to care about this, but not everyone does. Okay? In our case here, we have there's 2 different types of control systems that we typically work with. We have open loop and we have closed loop. Open loop systems have no sensing, essentially. They usually operate based on timers. You can use a timer in principle to do this hovercraft assignment, But that's pretty tough. We call it dead reckoning, where it knows when to turn around based on how many seconds have passed. And if anything goes wrong at all, like you just bump the wall slightly, it's probably going to throw things off. That's kind of like walking across campus in the middle of the night with a blindfold on and being given instructions about, or me trying to walk to the back of the room, walk off this stage with my eyes closed, getting instructions from somebody who says, okay, walk forward for 1.5 seconds and then step down. Well, if I get that even just a little bit wrong, you guys can laugh. Right? You guys are going to have a feedback system. You're going to have sensory input, and you have to figure out where you want these, which things you want, what types of things you can sense. When we talk about the Legos in a few weeks, a little more than a few weeks, you're going to see what types of sensors you have available to us. And you really have to make some hard decisions about how complicated you want your system to be. So at the beginning of class next week, we'll give you a couple illustrations to show you how complicated it can get. But until then, keep up to work. All right.